Our first speaker is Carlos Ordonez. Carlos was a theory group student and also a theory group postdoc. Okay, so Carlos,
Okay.
take it away.
Thank you very much for the kind introduction. It's always good to be back home. This is my intellectual home, but also my grandson lives here, so it's literally home. So we don't have much time, so I'm just going to tell you kind of the basic logic flow of arguments of this work. This work is an application of quantum field theory ideas that I learned here in the study of quantum gases at low dimensions. And it's another story for another day why I got to this point doing this. But it's been a lot of fun and surprisingly somewhat productive, as you'll see in the end in the community. So this, of course, is, this is in memory of Steve, and I share the feelings of appreciation and love for him that you all have. So these have been my collaborators over the years in this, some colleagues and students and postdocs, and at least a couple of real atomic molecular AMO types, as you'll see. Okay, and then let me briefly tell you the outline. It's kind of a long outline, but don't be afraid. It won't be too bad. So I always, have to do something for some reasons, and I'll give you the sort of heuristics and motivation for this work. I'll tell you about some previous work, and then some of the key results here are really general structural aspects, as you will see. And the anomaly, the quantum anomaly in this case, is equal to something called the tan contact, which is a very important thing in AMO physics. And then I'll talk about the virial expansion, and you will see how these things are all sort of come about. And then I'll just mention briefly some computational aspects. All right, sort of recap, and then perhaps the most interesting part is that out of this work came some interesting connections that were not seen before, and just mention some of the extensions and impact. Okay, so we'll see, of course, equations, but since I don't have time, you're free to contact me afterwards in Houston. I'm leaving shortly after today. So, but I'll be happy to interact with anybody in the future if there's any interest on this. Okay, so, okay, heuristics and motivation. So I came to these from many directions, and they're not all logical or sequential, but this is one of the motivations. So there is a very famous formula in atomic physics called the Bethe-Uhlenbeck formula to calculate the shift of the second virial coefficient in general for arbitrary gases with certain conditions, right? But in particular, in our case, I was interested in two-dimensional systems, and fermions could have been actually even bosons, but two-dimensional systems, which is something that these people do very well, and dilute, very dilute gases, so that the dominant interactions were just contact interactions in 2 dimensions. And if there is a bound state, right, then the Uhlenbeck and only that bound state, the Uhlenbeck formula, Bethe-Uhlenbeck formula is this one here. It has a piece from bound states, sort of the discrete piece, and then the continuum, the scattering part. This is the phase shift of the S wave, right? So if you know this, then you plug it in here and you get this formula. This is something that people knew in the AMO community, other people, how to compute the delta shift, the delta zero. And so this is the formula, right? So that's pretty cool. So now, if we don't have bound states, this first term would not be there, right? And then, so this is actually coming shortly, and then this term, in the case of no bound states and therefore scaling symmetry, so then this term would be 0. This, again, this is all sort of heuristic. So you would expect delta B2 to be 0 in that case. Right? So let's keep going. All right. So the case in point here is contact interactions between fermions in 2 dimensions, and the first quantized level is characterized by a Hamiltonian of this type. This is the Dirac delta function in 2 dimensions. G is a dimensionless coupling constant. And at the second quantized level in the thermal description, which I'm going to use, this is the Euclidean action, is something of this type. Okay, this is the sort of, and again, this is the same G. So this is what I have here, right? And it turns out that that there is a symmetry. There's a scaling symmetry in the action in both cases at the first quantized and the second quantized level. All right. There's actually a bigger. It's not just the scaling symmetry. You rescale t and x in this fashion, lambda some constant, and then it's actually there's a group. There's an SO21 symmetry. It's a bigger symmetry, but that's all well known. And so the idea is, again, as I said, if there is no bound states, so if there's a scaling symmetry, there shouldn't be a scale, right, of any type. Okay. So if there's a bound state, then I break that symmetry, and because there's now a scale. So due to quantum effects, due to the quantization of the theory, that's what we call anomaly. Okay. And so now, therefore, if there's no anomaly, there could not be a bound state, and this would have to be 0, and therefore I expect the delta B2 to be 0. That's the heuristic, right? So, by the way, let me say that these are non-relativistic quantum anomalies, which are not very well known by people who are more familiar with the relativistic case. These ones were found by Jacques himself, and so I'm following a lot of what he developed. So this is like, okay, so I want to know, and I have been doing some work on quantum anomalies following Jacques over several years, and I wanted to see if these ideas could be applied in some experimental context of, this is a possible connection here, right? So the question, right? So what is the relationship between the scale anomaly and delta B2? So again, naively, if there is no anomaly, delta B2 would be 0. But I know that if there's a bound state, and you can describe a bound state, and then there will be an anomaly, right? So delta B2 is not expected to be 0. All right. But what else can I say? Well, it turns out that the scale anomaly fully accounts for delta B2. It gives that formula. All right. When we do what I'm going to show you, we derive that formula entirely from quantum anomaly considerations, which is something that the AMO community hadn't quite done. But I'll say something about one person who actually did something, but this was not their view of what's going on. And then, so in doing this, I was able to again reproduce delta B2, but I learned a lot of things about the structure of these theories and the thermal aspects of the theory, and eventually, so I kind of picked up a framework, right? And then eventually this led to a very interesting application of these ideas to 1D systems. So I went down even one, which they can do. But now, so these are 2-body interactions. Okay? But now it's 1D and 3-body. And so we were able to use these ideas to this system in a very interesting fashion that I'm going to show. All right. So here is the sort of the triangle of, whatever, I can't. The triangle that, what are the connections between all of these things, right? And so that's what I did. So some history here. I have been doing work, just formal work, following Jacques, and I think I mentioned some of these things to David when I was at KITP a few years ago, which was a lot of fun. So we spent time with my colleague Horacio Camblon on systems like this one, but also 1/r² and others. And again, following Jacques, basically treated as a quantum field theory. That was sort of his thing, in which G can run, right? And then you can use that running to renormalize, et cetera, right? That was what Jacques proposed, and then he was able to, say, okay, so I can describe bound states using this, but then the symmetry is broken, so he called that a quantum anomaly. So following these ideas, we spent some time, several years, doing sort of formal things, right? And in particular, one of the so when Jacques wrote his papers, famous memorial paper, memorial to Bucky Beck, my former boss, he starts saying, okay, so there's an SO2-1 symmetry. This is the algebra, et cetera, and people know the algebra. But then later he describes anomaly. And my collaborator, Horacio, he had done some of these things with his collaborators in La Plata in Argentina, and for the 1/r² potential, and they connected to molecular physics, et cetera. So one time I was sitting with him and I said, well, this statement is not true, right? Because the algebra closed, right? And I said, because if you have an anomaly, you have to have an extra term. This is a scaling sort of conformal anomaly, right? From the string theory side, like these things happen, right? So then he was like, anyway, we went ahead and found that there is in fact an extra term, right? This is kind of like similar to the same thing that happens. I'm sorry, the same thing that happens more or less in string theory. And so we wrote a paper about this. And so what can we do with this? Can we test it? Can we use it in some context? All right. And so I started looking at the literature, and I noticed that yes, in the AMO community, they were kind of hinting at, they had the systems. They had produced precisely these two-dimensional systems where the contact interaction is the dominant one, and therefore it was symmetric, right? But nobody was sort of mentioning these things until I found this beautiful paper by Pytayevsky and Rush in 1997. Now, Pytayevsky, of course, is the same one from the Landau School, and Pytayevsky was now doing AMO, cold atom physics, and they realized very clearly that was a symmetry, conformal quantum mechanics, all those things, right? But when you have a two-dimensional system, that you have to trap it, right? They have this trapping term. So the trapping term, so you have a delta function, right? But you have to add the trapping term. And now the trapping term is not scaling variant, right? You wanted to do things with size and so on, all those. But then they realized that they were very cleverly able to find this sort of group kind of embedded in the theory by making some redefinitions, and they sort of got rid of this trapping term and have the algebra again there, right? And so once they have the algebra, they can use properties of group theory and whatnot. And in this case, and they call these hidden algebra. And in this case, they were able to reproduce qualitatively, at least, the existence of the so-called breeding modes beautifully. Because when I was starting to study this, you would open a book on atomic physics, and with due respect to it was a mess. The equations and well, so these guys did it algebraically very beautifully, like so they found these breeding modes, and they work like quantized, the lowest trapping frequency, et cetera, et cetera. So a beautiful piece of work. But then, so they had the delta function that was part of this, the two-dimensional, but they consider explicitly the repulsive case, right? They said G is positive, whatever. Now, in the repulsive case, you will not find bound states, right? They're never going to bind, okay? So I wrote, so what happens in the attractive case? That's the one I was interested in, okay? That's the one that gives rise to anomalies and all that. Well, they never addressed it. And I tried to find Pytayevsky, and I couldn't find him ever. So, but in any case, I was like, so finally, so I had it in my mind, and this extra term is a technical thing, but it's not so easy to handle as operators. But when you take expectation values, that's what Horacio and I did. We were able to show all the properties that it breaks the symmetry and all that. But in terms of the operators, it was not so easy to extract what the form was. But this fellow, Hoffman, a young student at Cambridge at the time, did it. But he did it in the context of cold atoms and a second quantization. So it was still, so he used the field theory version of this. And when you use the field theory, then you actually find exactly what this extra term is. And it happens to be this thing, okay? And this thing in the literature, he knew that it's called the tan contact operator. It's a big thing. This operator describes all or most of the thermodynamics of these types of systems, and it's a big issue for them. So this was a way. Tang is a genius. He didn't use it like derive it like this, but it was a nice connection from the point of view of symmetries and quantum anomalies. So this is the guy who really first found explicitly the connection between the tan operator and quantum anomalies. Of course, he referred to our paper. That's why, right? And so he realized that, okay, so Pythaevsky and Roche, he knew, of course, of that. They have predicted these frequencies, right? And so one of the consequences should be that was predicted using the algebra, the non-anomalous algebra. So now you expect some shift if you use this anomalous algebra. And so he went ahead and did some calculations, and indeed, in principle, you would expect shift in these frequencies, even of the order of 10% under certain circumstances and so forth. It turns out that it was more complicated than that, and experimentally, it took a while to really nail it down experimentally, and they did observe the quantum anomaly. But in any case, it was very interesting, and I got all excited about this. And so he also wrote very quickly some consequence on the level of thermodynamics, but he didn't, it was sort of formal thing, and he showed that the pressure for the system is not just equal to the energy density, which would have been the case for scale invariant, but it has this extra term. So clearly that's going to change the thermodynamics too, right? So I got, kind of somewhat depressed that somebody had beat me, but also excited that this is something that I was on the right track. So what I did was I then sat down and then, and he didn't use path integrals, and I am a path integral person. So I went ahead and looked at the partition function for this system. And then, having understood the pieces of all these things, I started studying the thermal properties, and by manipulating things here and there using dimensional analysis, etc., I was able to derive eventually the same thing, but at the level of the partition function. Sorry. This is the central result in that paper. So with the anomaly is the difference between, well, there's a 2 because it's convenient, but P minus epsilon. Again, if it's 0, there's no anomaly, there's symmetry, but it's not 0 and it's equal to this. And this was derived by us using this formalism. All right, so we are just making contact with this guy, but so what else? All right. So where is the virial expansion business here, the virial coefficient? What does this have to do with that? That's what motivated me. Well, then I went ahead and we computed delta B2. And there's a whole machinery to doing this. And I'm not going to bore you with, actually, it's kind of interesting math, Hubbard, Stratonovich transformations and all that this condensed matter people use all the time. I derived, okay, so anyway, so I found it. Right? So I found the delta B2, so it was all good. Then we found other applications and all that, but the most interesting thing here is that with this, we were able later to describe something very similar for 1D and for one-dimensional Fermi gases, but now with 3-body interactions. I'm not going to bother. Okay, so let's see actually quickly. Right, so this is what it is. It's that, right? And it turns out that this has the same symmetry, like classical symmetry. All right. And the question was whether the bound state structure was, known or not. It turns out that this is where I connected with my AMO friend that it is known. We can go to the center of mass, and it happens that it splits. The problem splits nicely into the center of mass, trivial, and a 2-dimensional problem exactly of the same form as the 2D problem that we had looked at before. So all the information about bound states, running of the coupling constant, anomaly is transferred here. So with this, we were able to get a new tan contact. This is our contact. That's okay. It's through the ends are the density operators, the number operators. All right, so we did that. And then one of the beautiful things here is that then we could relay directly features from the one-dimensional system with three-body to features of the two, okay? And so if you know delta B2, you know delta B3, for instance. We derive these things. You don't have to compute this. It's right there. So it's a kind of a duality or correspondence. So that was a very nice thing that we found. And this led to computational problems and things that other people have been doing. And so that's very nice. We also did some applications of this model, the one-dimensional model for transport properties with Jeff Mackey, a very, very bright young postdoc. And again, we use very structural kinds of analyses. And we got, so here the threes are the three-body 1D features. At the bottom, I have the bulk viscosities. And then here are the ratios between those two factors, those two parameters. And the two, of course, is again the two-body 2D. And here we prove this table. Okay, we proved that by formally, playing around with, and so now if you know whatever one of these, then you get the other one by this relationship. So that's a very nice way of not working hard. And so basically, we did this, and then this has been recently has been used by Japanese groups, and they're using it for Cooper triples in attractive three-component fermions, implications for hadron quark crossover. Just recently, 10 days ago, I saw it. So this has had some implications in the field, and I'm happy that it did, right? So, so basically, these are the conclusions. I use the methods that I learned here in quantum theory from the masters, and use it for AMO, and it has had some impacts. So I'm happy about that. And that's, of course, the funding agencies, you have to always acknowledge them, but the special thanks are for Dr. Fries and all the organizers here for putting together such a wonderful event and for gathering good friends. Well, thank you very much.
Questions for Carlos?
Since I don't think there's a lot of people in AMO here, can you tell us more about where this is important for AMO?
Yeah. So from my perspective, right, so this is a great question. And a lot of AMO people don't understand how to use these things, right? So, but some do. So what I had in mind was like for two-dimensional systems, right, they're not perfectly two-dimensional. There's a little height, right? So when you describe that, you really are adding an explicit symmetry breaking term to the Lagrange, right? But if you, but there's anomaly and there's that, right? If you're making a measurement, for instance, which is what, right? Which is which? You don't control. If they give me some numbers, I say, what is what is the dominant effect there? Is it the symmetry breaking thing, or is it an anomaly? They wouldn't know. So this, I thought of this as a way of having a framework that they can start, this is controllable. You can control the anomalies parameters, and they have these other explicit parameters, so they can play with these different parameters, but now with an underlying theoretical description. So that's more or less the broad picture. In the case of my colleague Drew, who's a real AMO in the condenser, he actually, this is the beginning for things like calculations of like phase transitions and all kinds of stuff in the field. So that's, Did I answer your question? Yeah.
So two questions. One, your anomaly was order G squared. So is there some kind of Adler-Bardeen theorem here, or would you expect higher order perturbative corrections as one normally finds when you have a conformal anomaly? And the second question had to do with the 1D case where you had three-body contact interactions, but evidently no two-body contact interactions. And is there some kind of natural framework in which you would forbid the two-body interaction?
Perfect. Let me
So
start.
those are two questions.
Yeah, perfect. Great question. Let me start with the last one because I learned that from those guys. So In general, you have both, right, in a system, but they are able to suppress one if they want. So they can just tailor three and so forth, but that's absolutely, and you can have both, but the mathematics gets a little, that's right. But they can do that, right? So that the first question is a more conceptual question, and I come from that background too, right? Tell you the truth, this just comes out. You just do you just do it, like Philip used to say, just do it kind of thing. For instance, if you just take the delta 2 potential, right? And then you just solve the Schrodinger equation and all that, you get the running and so forth. And then eventually this leads to the G squared term. So there's no like, I don't think there's like a loop expansion that then tells you that's the first order. It's just a non-perturbative thing. It's just exact, if you wish. Now, the G versus G squared though is interesting because I also like, okay, so this is not the interaction Hamiltonian because it had G squared. And it turns out that, so these are operators, but when you take expectation values, you use the Baird ground state or whatever, and then you make everything run, the coupling constant, cut off to infinity and all that. So the Baird wave functions, the ground state runs in a way that it has to be G squared, so to cancel and give you a finite answer. But it's a non-perturbative thing. It's not like this plus that. It's all non-perturbative normalization. So I don't know if there is some way of saying this is, but you just get the answer and just, it's and yeah.
Okay, so let's thank Carlos again.
Thank you.